We're going to look at a Q-switched ND-YAG laser marking system. These are very popular systems. They've been around a long time. The first one I worked on was in the mid-70s at a company called Corad. The list of applications for laser marking is endless. They do everything from product code marking on both metals and non-metals to design work, say for example putting designs on knife blades. I mean it's literally endless where laser markers are working today. Probably the biggest trend that's been happening, and it's been happening for a while, is replacing Q-switched YAGs with fiber lasers. So if you have a fiber laser, this analysis is going to be almost identical for your fiber laser, except there might be a little change with the wavelength. The wavelength might be around 1070 instead of 1064, but there's not going to be much difference after that. Everything will be the same. So let's get started. We have a 1064 nanometer wavelength, repetitive pulse, average power is 10 watts. We have a 100-second pulse duration, 100 nanosecond pulse duration. Let me stop here and point something out. If you don't know what the pulse duration is, don't worry about it. Q-switch lasers run in the nanosecond range. Now, if you look at the MPE table, and that would be table 5F, line 1050 to 1200 nanometers, the exposure duration line is going to read 10 picoseconds to 13 microseconds. You're going to see that from 10 picoseconds to 13 microseconds at a 1064 wavelength or 1070, that the MPE is the same across that entire exposure duration. Okay, so if you don't know what the pulse duration is, pick one. And we typically default to around 100 nanoseconds. That's going to put you really close, and if anybody is scrutinizing your report, they might say, if you put something like 20 picoseconds in, and somebody kind of had a clue as what they were looking at, they might say, well, that doesn't look right. So we say, well, yeah, default to something in the nanosecond range, 100 nanoseconds, and that's going to give you a number that's going to be comfortably close to whatever the real value is. But it's really based on the standard. So take a look. That line is going to be 2 times C sub C times C sub E times 10 to the minus 6 joules per square centimeter. C sub C, which is right here, if this is switched to C sub A, just click it. That'll give you C sub C. C sub C is 1. C sub E is, we're going to set that to 1 because we're wanting the point source MPE, and so with all that said and done, our rule 1 MPE will be 2 times 10 to the minus 6 joules per square centimeter, and here it is right there. So yeah, just remember that set that pulse duration somewhere in the nanosecond range, and 100 nanoseconds is a really nice spot to land on. We have a pulse repetition rate of 50 kilohertz, and that 50 kilohertz is running the top end of what a system like this will run at in rep rate. Okay, but for this example, we're looking at 50 kilohertz, and there's kind of a little bit of a reason why we're doing that. We'll get to in just a minute. The exposure duration is the ANSI default, which is 10 seconds for an unintentional or accidental exposure to a near IR wavelength. We have a beam diameter at waist of 5 millimeters, divergence of 1 milliradian, we're 1 over E squared, circular Gaussian. Set our observer range at a half a meter. That gives us an OD at observer range of 3.7. Worst case OD is 3.71, which leads us right over here to take a look at the transmission through the limiting aperture, which is 7 millimeters for the eye, 3.5 for the skin, and we can see we've got about 98% of the power being transmitted through the limiting aperture, and that's why we have a little bit of difference here. The NOHD is 713 meters. The NSHD is 50 meters, and of course that's really being driven by the MPEs. The ocular MPE is 5.06 milliwatts per square centimeter. The skin MPE is much less restrictive, which is 1 watt per square centimeter. So we ask ourselves, well, is this laser a skin hazard? It is 64.5 times, the irradiance of the laser is 64.5 times above the MPE. So yes, This is an extreme skin hazard. If you put a piece of material in front of this laser, it'll probably ignite it, which means it would probably ignite you too. So be careful. You don't want to put your hand or something in a YAG beam. Not a good idea. Let's see. What else do we want to talk about here? Let's talk about the diffuse reflection. Since this is a marking system, typically they're enclosed, except right where the marking head is, where we're marking the material, because a lot of times we're marking, unless this is a dedicated production line system, it won't be fully enclosed around this marking head. If this is something, say for a job shop, we may have the marking head open because we're putting different sized parts in, and so we don't have an enclosure right there. So we care about the diffuse reflection, and when we calculate the diffuse reflection hazard, we always do it in our worst case. So the spectral reflectivity will be 100%, viewing angle will be 0. We'll do a small beam on target so that we get a point source, because we are in the near retinal, we are in the retinal hazard region. Observer range, we'll put it at 1/4 meter. Exposure duration is 600 seconds. The ocular MPE is the same as for the intrabeam, and that's because it's the same MPE for 10 seconds and 600 seconds. We have an OD observer range of realistically 0, but this little bit of OD comes from the fact that our NHC is 2.51 times 10 to the minus 1 meters, or let's see, that would be just over 1/4 meter, and you can see we have our observer set at 1/4 meter. If we put our observer back just a little bit more, yep, goes to 0. All right, so 0.25. All right, so we really don't have an OD at observer range, but if, of course, if we were running this in more of an open beam situation right around where our mark is, of course we'd want our operator wearing eyewear. Be a little short-sighted if we didn't do that. We can look at the scan information here for diffuse reflection, and we can see that, yeah, there's nothing to worry about here. We're well under 1, so there's no diffuse skin hazard from this unit. Most of the time for the marking system, what we're really interested in is the lens on laser here. So we have a 200 millimeter focal length lens. We're using the beam diameter that is at the beam waist. We can even see over 1/2 meter. It doesn't change much. So yeah, put 5 millimeters in here. The only reason this would be any different is if there was a small beam expander, maybe a 2x expander in the system, in which case we would be using 10 millimeters. But for this particular laser, we're saying, wow, we're just coming out with 5 millimeters and then bringing it through our focusing lens, making this a little easier to do this analysis. But like I said, got a little beam expander in there, a 2x. Yeah, we'd put 10 millimeters for the diameter here. We set our observer at 1/4 meter. Now we get a OD at observer range and a Lenso laser NOHD of about 28 meters. What I'd like to do is look over here and take a look at our Rule 1 MPE, as we've already looked at. It's 2 times 10 to the minus 6 joules per square centimeter. Our Rule 2 MPE, after being adjusted to be able to compare it to a single pulse MPE, or the Rule 1 MPE, it is at a little over 1.01 times 10 to the minus 7th joules per square centimeter. So that's the reason the software has selected Rule 2. This is the most restrictive MPE. Let's change this to a radiance, which we've done, and we can see, sure enough, this is the same MPE as we have here. If we look at the AEL, we have almost 2 milliwatts allowed exposure for a 10-second exposure here. And of course we can look at the same thing here and we'll get the same result that we see here for AELs. Let's switch this back. Okay, you know, something that would be kind of interesting to look at here is something called the crossover frequency. It's the frequency that if this laser is running, that if we increase it just a little bit, say 1 hertz or so, the system switches from rule 1 to rule 2, or if we're going down in frequency, it switched from rule 2 to rule 1. That's what the crossover frequency is about. So let's find that crossover frequency. Okay, I'm going to take a really wild guess here. Let me look at 2,530 hertz and hit that, and notice we changed to rule 1, and notice that the MPEs look almost identical. Okay, so when they're the same, it doesn't really matter whether you choose 1 or 2. The system picks one and says, yeah, this is the one we're using. Let's go to 2531, hit that, and you'll notice that, yeah, that's the crossover frequency between 2,530 and 2,531. When we make that 1 hertz step, it switches to rule 2. That's the crossover frequency for this particular analysis. Okay, and that's what crossover frequency really means. What's that frequency where we change from rule 1 to rule 2, or rule 2 to rule 1? Okay. One last thing I think we want to look at here is if we had to do some servicing on this equipment and we had it apart and we needed to set up a temporary class 4 laser control area, what would our barrier need to see? And let's say we're at, I don't know, 1.75 meters. We've measured it out. That's where our barrier would be. Let's put that in here. And let's put 1.75 in here, and look what we get. If we're looking at the intrabeam, we'll want to go to 1 over E. Remember, barrier specs are in 1 over E. We would want something that would be about 90, we'll call it 100 watts per square centimeter, but if you told your vendor 90 watts per square centimeter, I think there are barriers that would be perfect for this at this distance. They're 100 watt per square centimeter barriers. And now, what about the lens on laser? Well, the lens on laser at 1.75, remember that this would be a much higher divergence than what we see in the intrabeam, so it's only 1.32 watts per square centimeter. Let's take a look at radiant exposure, and we would need to report that for an intrabeam exposure, we'd have about 36 millijoules per square centimeter, and we'd have about a half a millijoule per square centimeter for the lens on laser. That's what we'd want to tell our barrier vendor. Okay. Calculated values: average power 10 watts. We got that. Peak power is about 39 kilowatts in that pulse. So yeah, it's got a nice little pulse to it. Energy per pulse is calculated out to be almost 4 millijoules per pulse, and it's running a duty cycle of 2.5 times 10 to the minus 2%. Looking at everything, I think that's about all we need to talk about here. Okay, that's it.